Thank you very much.
Okay,
I do
thanks.
appreciate the opportunity. Hello, everyone. As Professor Buchanan mentioned, I am a student under supervision of Professor Buchanan. I received my doctorate on cybersecurity analytics from the George Washington University. I'm also founder of CyberSec. This is a cybersecurity and quantum security startup. And also, I'm a big fan of Turkish baklava. And right now, I'm doing research in Edinburgh Napier University. I like to share some insights about quantum computing and the intersection with cybersecurity, specifically with post-quantum cryptography, with you today. And please feel free to ask questions. I will try to catch some of them during the discussion, and also the rest at the end of our discussion. So with that said, let's start with two stories, not a very big deal. The first story is about quantum computing, and it's quite important story because this can change. This is the future of computation. From one aspect, we are developing high performance computing and new processors that can support artificial intelligence development. And from the other perspective, we are developing new type of computations like quantum computing. So it's really fantastic if you devote some resources and learn about quantum computers. And I'm intending to right now give you an introduction about the status quo. So let's first start with the different ideas that at the current time you can see in quantum computing market. The first type is superconducting qubits. And by superconducting qubits, we mean a type of design that it's very circuit-based, and it utilized classic superconducting circuits, and it must work close to zero temperature. And also big brands like Google have offered some practical proof of concept for that. So they are working on removing barriers that I'm going to explain for you. This one is Velo processor that supports 105 qubit. And this one is Heron R2, which is also offered by IBM. IBM right now supports 433 qubits and promise to deliver 100,000 qubits by 2033. So this is the first type. The second type is photonic quantum computing. Brands like PsiQuantum or Xanadu are working on that on US and also Canada. It employs photons, light particles, to encode and process quantum information. And it works also usually in room temperature. This is a big advantage. There are some highlights. Recently, we have seen that it can be migrated to a scalable and fault-tolerant photonic quantum computing capacity. And already there are some sort of NISQ or noisy intermediate scale quantum capacity available in the market. The third one is neutral atom qubits. I can probably show you a little bit about this today to you. Quera is one of them. Pascal is another vendor. This technology leverages neutral atoms trapped by optical tweezers, and also it offers reconfigurable qubit arrays. So in Caltech and also Quera, we have such an implementation right now. Probably still AWS give you a good access to early qubits on that. And today, I'm intending to show you what Microsoft can offer, but perhaps you can also do a research and develop your journey to see how Quora works on AWS. The other one is Marijuana or Marijuana 1, which is topological qubits based on Microsoft. It's very scalable, and also it can encode qubits in topological states of matter and potentially offering inherent error resistance. So this is the pathway that Microsoft follows, and offer also some promises to make a scalable, faulty-tolerant quantum computers. And the last but not least is trapped ion qubits. And we have IonQ and Quantinuum right now in the market, offering a good number of qubits. Quantinuum is UK and a US brand, and IonQ is US brand. They're using ions confined in electromagnetic fields and manipulated with lasers to perform quantum operations. So there are also recent developments. They have offered randomness, certifiable randomness, that is very important for us in cryptography. And I'm going also to address some points about that today. So right now, there are vendors actively working in the market, and they are offering quantum computers with limited number of qubits, and it's already accessible for you. So you can just, make an account in Microsoft Azure and try to learn and practice with qubits and quantum computing right now, or use simulators and for free use simulators like AER that is offered by IBM and Qiskit platform, and try to learn quantum computing. It's very recommended for those who already started their journey for cryptography and wants to see what could be the future. So this story, is a big one, and we will learn about that in future a lot, and we will hear about that a lot. Uh, Annealing is not indeed a type of quantum computing that we expect. It's very well designed for optimization problems. And D-Wave is the unique provider right now. They have offered 6,000, and recently they offered more in terms of number of qubits. So it's very good to run such a specialized optimization problems on this type of annealing or quantum annealing computers. So with that said, I just want to bring this into your attention that there are already some brands actively working, and there are some quantum computers from simulator to real noisy intermediate scale quantum computers that you can deal with, and you can start trying to design different circuits and learn how to deal with this. So let's start with some basic concepts that is important for our demonstrator. The first is, what's a qubit? We talked about different type of ideas that physicists offer to make a qubit and quantum computers. But what is a qubit? Qubit is the fundamental unit of quantum information. And unlike classic bit, it is covering a big space of information. So it's not either 0 or 1. It can be formulated as this way, and psi can represent two complex numbers that has a specific property, which is this one. And then we can show a big space or block sphere that show all possibilities beyond the state of 0 and 1. This gives a lot of computation capacity, and in contrast with normal bits, it's a very different concept. It needs a lot of new understanding and learning about how parallel computing works and how this new technology and new algorithms can help us to solve complex problems. One of good practices is to use tools like blockcurve.io. Let me show you that to learn about this type of concepts. So this site, as I mentioned, I'm also, I hope I can share it in chat with you. So please, at your convenience, invest time and see how the block sphere or one qubit offers you different possibilities. For example, you can rotate the position of the information on one qubit on different axes, X or Y or Z. So it's possible that you rotate it. Let's do the initiation. Please confirm if you see the website in chat with a yes or no. Do you see? Okay, thank you. I see that at least someone sent a heart for the website, but do you see also the website that I'm showing you right now? Please. Okay, thank you. Thank you. So yes, you can change different parameters of a qubit and see how theoretically it works. This is a very good tool to deal with that and see how information will be mapped to qubits. So a part of research is how to encode the information, the normal information into qubits. And we have different type of circuits and feature maps that helps to encode information in quantum state. It's very important because, for example, if you can turn image to quantum state or to quantum format, then you can encrypt that image. Or if you can bring the data into quantum format, then you can do quantum machine learning and do some processing on that. So this is a very good tool that you start to learn and see how different concepts can help you to generate some hypothetical concepts over a block sphere. Quantum gates also, I like to talk about that, specifically Hadamard gate. So let's talk about Hadamard gate a little bit. So we have a lot of gates that they're helping us to design specifically a specific purpose circuits or hardware designs, or configure the quantum qubits in a way that we want to see the quantum information processing happen. And the Hadamard is one of the very interesting one because it brings the information in superposition. So the information will be both and 0 and 1. So that's very interesting. Let's come back to our block sphere demonstrator and use Hadamard gate. So this helps that you have this information in both 0 and 1, and helps a lot to bring the quantum computers in the state of superposition. So with that said, I just want to bring this into your attention that when we have a quantum bit or qubit in superposition, it means that if this is designed in a right way, we have 50% chance of being in 0 or north pole, and 50% of chance to be in the same time in south pole of the block sphere. And this is a very, very interesting, capacity. It is useful for quantum key distribution. It is useful for quantum circuit designs. So this is important to see how this works on real quantum computers. And this is why I'm intending to right now show you how to run a Hadamard gate on a quantum computer like IonQ or Quantinuum. I take Quantinuum because you can do it freely yourself. What you need is just to make an Azure account. So what you have to do is to just go and make a Microsoft Azure account. And when you do that, then you can request a early free credit for quantum computation. You have quantum workspace on that. And in quantum workspace, you can generate an area that you can bring your quantum computations into that area. So when you make a quantum workspace, I have a lot of them right now here. I'm going to what I prepared for you as Trust4Future. You will see a set of features like this. The first thing that you will see is a notebook for Python programming. The good point is that all of the quantum programming languages like C sharp, Q sharp, or Qiskit or Cirq, all are indeed Python libraries. So you can make, for example, IonQ, or you can make Rigetti, or you can make Pascal. Even Pascal is accessible. It's atom-based quantum computer on Azure. So Quantinuum is the one that you can do it for free. So let's show that to you. Let's do a hello world on Microsoft platform. And in this hello world, I just bring this into hide mode that you can see. First, you have to do some setup when you make your account and when you make your workspace, quantum workspace. You will receive a subscription ID. This should be kept, confidential, but it's not the only parameter that you need to get into the quantum space. So therefore, having this ID is not a security risk in general. But you have to bring this as a prerequisite, and then you can connect to your workspace. When you connect to your workspace, you can receive the quantum computers available to you. When you make a free one, Quantium Simulator and Emulator will be available for you. But the difference between simulation and emulation is that simulator is fault tolerant. It means that there is no noise, there is no error. It works in ideal condition. And we can really simulate quantum computers with 30 qubits on normal computers. So from that perspective, if you have a problem that is solvable with 30 qubits, it's already solvable on normal simulators on quantum computers. And this is one of the main techniques these days, because you have data dimension reduction techniques in statistics that you can reduce the dimension of data, and therefore you can run some sort of experiments with lower number of features on simulators. But emulators are very close to the hardware, so they simulate all noise, errors, and problems of the hardware. From that perspective, when you have Quantium emulator as backend, then you will see the real hardware experiment. So this is what I can do right now with two workspaces, simulator and emulator. And you can see the capacities are available here. I have access, for example, to 20 qubits on this one, or 56 qubits on the other one, or 20, 56. So these are the practical ion-trapped devices that even I can run a real experiment on that with the normal QPU or quantum processing unit. I have to just change the backend and pay the cost if I do not have research credit for that. You can, of course, with the principal investigator, request a research credit and have access to real QPUs. But to be honest, to share an experience for years of working with this type of quantum computers, it doesn't really matter to bring your experiment on real quantum computers, basically because they are noisy and they're slow at the current time. This is a cloud-based deployment. So from my laptop to the telecom infrastructure that connects me to the Azure data center, and from Azure data center to the quantum computer deployed in some data center in the US, there are a lot of links, and there are a lot of also cryptography applied for TLS connections and session management. So these TLS sessions will be renewed and the connection will be lost. Therefore, this table running for over 24 hours needs a lot of hardening. It's truly a hard task. And therefore, if you stay with simulator, it's far better, and you don't need to run big circuits with high number on real computers. So let's make the first Hadamard gate. You can see that we can define the circuit. This is just one qubit, and the qubit at the end will receive a measurement, which means that it will come out of the quantum state. So it is not anymore at superposition. So it will become something, and we measure that on a normal bit, and we report the results. So the circuit here is something like this. So it's one qubit, we have one Hadamard gate, and then we have the measurement, and the result will be stored here. So you can now submit this to the backend. So those backends that are available to you could be selected here for free. and you can submit it to Continuum Simulator H11E or emulator. And then you run it. It's like old days, you know, when I started computer science, it's about 3 decades ago. I was doing, you know, something in our faculty, and then the main data center was something, you know, far from the main faculty. So we could receive the result of our computation, for example, at 5 p.m. In printed format from that data center. So this is like that. So this is generating a job ID, which means that right now I have a circuit running here. So let me show you. If you go to job management, you will see your circuits. So this is my circuit, and you can see it has an ID. The ID is CA something. So if we come back to our example here, you will see that job ID is also that CA something. So you will pass your circuit to the quantum computer through that constellation and setup that I explained. And the quantum computer or simulator or emulator run your circuit and then turns back the result to you. So let's do it again and see the big picture very quickly. You will make a quantum workspace first. So you need to make a free Azure account, a free quantum workspace, and then a free Continuum access. And then you can just connect to your workspace, then check the availability of the workspaces, and then select the workspace that you have already access to, and then design your circuit and submit your circuit, receive the job ID. When you have the job ID, when the job ID is done successfully, you can then receive the results. So practically you can see if it was 50% on North Pole in the qubit or 50% on South Pole, or it was a little bit different. So in this example, you can see it was in zero ket position for 46 times in 100 shots and 45 times on one at the result of emulation. So it's relatively good, but the pure one should show us something like 50-50. So you can do that. I like also to show you more that you can also connect this environment to your Colab environment and combine it with some cryptographic concepts. So before moving to very deep details about cryptographic concepts, let me show you how to connect it to your environment on Colab. You have the possibility to use 800 or other type of runtimes based on the computation capacity. And this is very important feature of Colab because it can give you a fast computation when you need to simulate quantum behavior. You need to install Azure Quantum. When you install that, then you can receive, if you have the credit, you can receive more machines. I already have access to more research credits, so I can see more machines here. For example, Real Quantum Processing Unit ARIA 1 and ARIA 2, which are quantum machines, very good quantum machines. You can see their number of qubits, you can search about them and learn about them. So this is IonQ ARIA, and you can see the details of IonQ ARIA here. So with that said, I have to select one of these machines, either Quantinuum or Rigetti, which is another technology, and IonQ. And then when I have, again, I can just make a simple circuit to bring the qubit in superposition with a Hadamard gate, and then draw the circuit to become confident that this is the circuit that I like to have, and then run it. So that's the same story. I can run it right now with this code that show all possibilities. So I select, for example, for IonQ simulator. So I select 2. And you can see when I select 2, then I have a job ID called 75EE something. And let's go to Microsoft and see where is that job ID. So this is not in Trust4Future. Trust4Future is made for you for Quantinuum. It is in another workspace. So in this workspace, you can see that I have access to all of these quantum computers, and I can go to job management. And in this job management, I must be able to see that 75EE, which was our quantum circuit. So if I move this quantum circuit to more details, then I can see what is the circuit name, what is the ID, what is the provider, what type of simulation or emulation or real QPU is applied there, what are the number of shots, what is the other specification like time, how long does it take. You can see it takes, for example, started submission time was 48 and completion time was 56, which is not good, because if you are running, for example, 1 million circuits, then it means you have to wait 1,000,008 seconds, which is not doable. So you can have a lot of details with this type of log management, and sometimes you can see also things could fail because of those complexity in runtime, maintenance, and also the session management, the availability of the architecture on your end, their end, and a lot of other impacting factors. So you can run this type of circuits with Colab. And let's come back to Colab and see the result on IonQ. In IonQ, that circuit gives me 50-50. This is simulator, so this is very ideal fault-tolerant quantum computer. So I can show the result, and this is a very perfect logical qubit demonstrating superposition. I can also play with Python and change, the demonstration in other ways to show the level of things. Also, we have to learn about different architectures, because different quantum computers have different hardware and different gates. So it's a learning curve. When you're dealing with quantum computers, you have to, over time, make yourself familiar with the details of the gates and availability of the, everything on that specific hardware. So with that said, I just want to show you another circuit, which is relevant to our topic. And this circuit is this giant circuit. It shows 8 bits or 8 qubits. B for measurement. Of course, this is qubit. After measurement, this will become bit. So in this circuit, this is a long circuit. You can see this long circuit. In this circuit, I'm intending to generate a random number, a quantum random number. And this is the reason that we will go to next story. But before going to next story, I'd like to elaborate more about this one. Take one question from the chat and then continue to our next story. So let's see, what do we have in the chat? Any question? So we do not have question. If you have, feel free to send it. Otherwise, let's continue about the timeline of quantum computing. So when you are doing a research and when you're developing your skills on a specific technology, it's very important to understand the timeline, because it is an opportunity to be a part of generating the future yourself. And also it could be a threat if you're expecting, for example, an immediate job, like, for example, developing mobile application. It's not happening. Therefore, it is important that 2025 is year zero. We, at the current time, expect that high-performance computing centers and data centers can simulate strong quantum computers in the next 3-4 years. And noisy intermediate-scale quantum computers, like I showed you, IonQ, Quantinuum, Pascal, Rigetti, all of those things, received a lot of research and design and research and development for scientific exploration. And then we move to an area which is post-Q. And post-Q means that after that, we are expecting to transit to fault-tolerant quantum computers. So about 5-6 years from now, we are expecting to see scalable fault-tolerant quantum computers. After 10 years, we expect to have really scalable commercial quantum computers that can even break cryptography. But this timeline is about availability of quantum computers for everyone as a commercial computation capacity. It doesn't mean that cryptographically relevant quantum computers could not be achievable sooner. Before I elaborate that, let me show you what are the obstacles for commercialization and making scalable quantum computers, and then I will talk about cryptographically relevant quantum computers. So at the current time, this paper is a very useful paper. I like to ask you to read it because it gives you a very realistic understanding of all barriers. I'm not going to elaborate all. It's summarized for you here. But we have system engineering and physical layer problems. We have hardware level challenge. We have software and compilation challenge. We have algorithmic and application and use case challenge. We have also intermediate to utility scale challenge and also economic and infrastructure challenge. So all of them should be solved to have, for example, 100,000 qubits operating, for example, per country and become accessible to commercial use cases or scientific use cases at the scale. And at the current time, the biggest one is quantum error correction. And quantum error correction is a big barrier because we can extend the number of qubits, but the noise and the error will be huge. And therefore, at the end, the result of theoretical computation will be very different from the, what we expect and what we will observe from the real implementation. So quantum error correction is a bottleneck right now, but it doesn't mean that we do not have other problems. We have also problem for quantum data in transit. We have also problem for quantum memory. We have also problem for mobility of quantum computers. Therefore, there are other technologies and emerging technologies are coming to solve and address those challenges. So these barriers should be solved, but governments and researchers in cryptography especially are working on cryptographic relevant quantum computers that they are showing the possibilities for running either Shor variations or optimization variations to break RSA and ECC. So let me a little bit give you insight about Shor variations and optimization variations. Shor algorithm, we know it. We received a very good lecture from Professor Buchanan, but there are efforts. For example, this paper on 2024 and 2025 that they're trying to reduce the number of qubits and reduce the capacity needed for breaking RSA. So these two papers, they are promising that they will break RSA 2048 with 1 billion qubit. This is what Google proposed. And the other one is with 372,000 qubits. So these are very big change in number of qubits. The estimation is that in 9 hours, this will break the RSA. The other one is in 16 hours, this will break the RSA. And also they're expecting quantum error correction because otherwise bringing that over the chip and make it scalable will not work, is that 0.1% physical error happen. It means that there is a difference between physical qubit and logical qubit. Logical qubit or pure qubit is something that has no problem, no noise, no error, will be needed around 20,000, but physical one with this error rate will be about 600,000 to 1 million qubits to give you those pure 20,000 logical qubits. And similarly, here we have 372,000 physical qubits that will give you 3,700 logical qubits. But the worrying here is that with the recent developments on hardware, you can simulate one qubit on, for example, one NVIDIA A100. And therefore, if you have a good technology, that I will address one of the good ones at the end, you can have 3,700 simulators right now operating in a data center. Therefore, these algorithms, in theory, can break the RSA right now if enough resources are allocated to them. But as I mentioned, they are not anymore noisy intermediate scale quantum computer, but they are FTQC or fault-tolerant quantum computers. So the optimization variation also is about another pathway that people are working on, ideas like what Professor Schnorr offered for fast factoring of SPP algorithms. Lattice you learned in this course is a algebraic structure, and this is something like a grid. And a shortest vector problem in lattice structure is to find shortest non-zero vector, which means that you have a lattice as input, and you have to find among all points in the lattice the closest one to zero. So if this problem could be addressed, it's a hard problem, then with the setup Professor Schnorr offered, in theory, RSA can be broken. People try to implement this. According to reports, I didn't touch that, but what I read from very credible cryptographers is that the parameters proposed here could move forward. Therefore, people try to bring quantum computers and optimization capacity of quantum computers to finish the job of SPP algorithm for fast factoring integers. One of them is proposed by Chinese for 372 qubits, physical qubits, which means 37 logical qubits. But honestly, the circuits were received from them under supervision of Professor Buchanan, and we learned that this is workable for just very tiny numbers. And then Google responded and said, okay, this is not only about size of numbers, but also it's about the quantum machine learning and quantum optimization algorithms, mainly the limitation of quantum approximation optimization algorithm, which cannot solve these big optimization problems. So they reject the claims that that paper made for 372 qubits. Later, Russian researchers tried to also make cryptographic relevant quantum computers and show how on ion-trapped quantum processors they can break RSA, and they just could do very small numbers, and you can see this is very small results with 15 qubits. And then they reported that the problem is actually the QAOA, because this optimization algorithm has theoretical limitation. And then other people started to move to variational quantum algorithms and develop it further. So the first story coming to an end here, I just want to give this main takeaway. And if you have questions, please share in the chat, and I move to the second story. The key takeaway is that quantum computers are operating right now. You can run them on simulators. You just need to learn Qiskit. You can just find Qiskit Summer School 2025 on IBM. It is not yet full, so you can be onboarded and learn it in July. And within 2 weeks, you will be quite professional in Qiskit and different type of quantum algorithms, and different hardwares also are accessible. Timeline is 10 plus years, but cryptographic relevant quantum computers is another topic, and it could be sooner. And it is something that researchers and cryptographers and governments are investing on that to see on what time we have to assume Q-day is coming and the migration should be done. At the current time, everyone accepted that by 2030 we have to move on. And now let's start the second story, which is about migration to post-quantum cryptography. Any questions so far? Okay, so next, you have heard about different type of quantum safe cryptography from Professor and other lecturers. So hash-based, code-based, multivariate, lattice-based, and isogenous are different approaches. And already some of them received a standardization. So at the current time, MLDSA, MLCAM, LMS, XMSS is a shared area of agreement for all authorities. And all authorities have a common understanding that these algorithms are reliable enough and we can move to migrate our current cryptography to the hybrid mode and then post-migration. Post-migration means that you have to see optimization bottlenecks, implementation and design flaws, hardenings, troubleshootings, and different things. So with that said, future hybrid quantum cryptographic algorithms will be something like this. You shall not be surprised if you see, for example, a TLS, which use elliptic curve Diffie-Hellman and Kyber, or RSA and lithium, and then AES, and then with GSM mode and SHA. So this is happening, and we are expecting that on digital signature and on key exchange mechanism, migration to be happening. Already some vendors like Samsung or some vendors on TLS certificates and TLS channels have migrated, and they offer the migrated solutions like Google. So we have these efforts ongoing. But to bring this into your attention, the standardization also is in process. So already we have FIPS 203 for MLCAM and 4 and 5 for digital signature. We have also European approval for cryptographic mechanisms, April 2025, provided by ENISA, and also CNSS, which is about top secret cryptography for US government. And you can see also they have approved, for example, MLCAM. So with that said, we are also expecting to see FIPS 206, which is about the algorithm number 5 for key encapsulation. Devil is in detail always. So when you go to implementation, this is a paper and research under supervision of Professor Bill. So we will make it available very soon. When you go there, you will see that the algorithm has a sequence, the standard has a sequence of calls. And these sequence of calls are relying on random numbers. So this is a problematic area. We have proven mathematically and practically that these random numbers are truly important. And therefore, for top secret or secret for level 5, anyone wants to use, for example, Kyber 1024 or DSA 87, they really need to have trusted implementation and trusted source of randomness. And this is the quantum opportunity. So with this part, I'd like to just say goodbye to everything relevant to quantum threat and talk about quantum opportunity. So one of the opportunities that quantum computers can offer in the same time is that they can make true random numbers. And at the current time, there are standards, and everyone use these standards, for example, SP 890A, which is very good for deterministic random bit generation. And it is applicable in all cryptographic libraries we are using these days everywhere. But for more serious use cases or for long-standing cryptography use cases like blockchain, we need to either bring crypto agility, which means that we have to be able to change the key size or tweak the cryptographic parameters, or we have to design a system that lasts for 50 years, 100 years. So when it's relevant to blockchain or long-lasting digital assets, decentralized one, then we have to move to a stronger type of randomness for those parameters. This is where we have SP890C and SP890B, which is just about the entropy and the source of entropy and validation of that. So you can see people are trying to show that first, for example, their technology like Quantinuum that I showed you, and you have access freely to that, made in UK, has the capacity for certified randomness. But it doesn't mean that it's a done job, and we have to, do a lot to make this happen. I like to bring this to your attention, that what will be the future of quantum enhanced post-quantum cryptography as an opportunity. So here we will design a circuit, and this circuit will bring us a randomness, and then we use those random numbers in our algorithm. That's the idea. So with that said, I just want to show you one quick demonstration. This will become available fully on our conference date on 24th of June. So I hope we see you there. And on that day, I will show you a new technology that can really support the idea of quantum enhanced post-quantum cryptography. And this is quantum brilliance. Quantum brilliance is a portable diamond-based quantum accelerator technology, very different. It has some merits. So under supervision of Professor Bill, we are working on this technology right now. And in Luxembourg, we are hosting big number of qubits to generate random numbers. And it utilized nitrogen vacancy centers in synthetic diamonds as qubit. And it operates in room temperature. And also it's enabled to have very small scale quantum processors, which means that you can have in a laptop size a quantum computer, and you can have qubits that you can put it in your racks very easily. It's very promising technology. We have right now a collaboration and research agreement, and we're working on that to make a demonstrator fully available for you. I'm going to show you how this will work. Right now, I'm not sending the email, but please keep the web address. And on 24th of June, you can test it and receive a digital signature supported with quantum randomness and encryption supported with quantum randomness with this technology. So this is the way. Quantum brilliance, quantum constellation will generate secure entropy vault data for us, and we keep it in our secure entropy vault. This is a very specialized key vault to keep those things securely. We have a statistical long pipeline to test their randomness, certifiability, compliance with these requirements, and also German AIS requirements. And then this will be used in our demonstrator. So let me show you the demonstrator, and please keep the address. This is the address. I'm sharing that in the chat, and you will see full functional integration on that day, and I'm open to your questions. So here, you can write your email. Right now, as I mentioned, we are not sending that, but then you can write your message. This will be encrypted and also signed, connected to those source of randomness, and you will receive it in your email. Right now, of course, it is not connected, but you will receive it in your email, and then this is the demonstrator that the MLChem or modular lattice-based key encapsulation mechanism, and also digital signature can be truly empowered with source of quantum randomness. So that's all for my presentation, I would be happy to take some questions, and thank you for the opportunity and having me, Professor.